My name's Ben Redman, and you might actually notice there's two names up here on the presentation that Chris just introduced you to. Hadi Moshe Eddy is actually the principal developer on our CStore FDW extension, and CitusDB is a company that was actually founded in Istanbul, and so he works out of that office. So unfortunately, he couldn't be here today, but I thought I'd give him some credit. And if we go over to the next slide here, oh, that didn't work. Oh, there we are. 1 second lag. So that's Hadi on our trip recently. Actually, I flew here from the Aegean, where we were sitting on the shore at our first dream retreat talking Postgres. So if you're a Postgres developer that's interested in this sort of thing, definitely talk to me. But yeah, so a bit about me. My name is Ben Redman. I'm a software developer / solutions engineer / sometimes public speaker for CitusDB. And I've been at the company for about a year, and I worked before that at AWS with one of the founders at Amazon for a number of years. So today what we're going to do is I'm going to give you a talk, describe CStore FDW, our analytics columnar store foreign data wrapper that we built for Postgres and for use in CitusDB. And so what that means is that it plugs into, as a regular Postgres extension, can use the foreign data wrapper technology. How many people here have used foreign data wrappers before with Postgres? Okay, so a few, but not a ton by any means. So they basically let you take an external data source and make it look like a regular table in your Postgres database. And so that means you can connect your PostgreSDB to almost anything that you're willing to program to. So in this talk, I'm going to discuss, first of all, why our customers wanted columnar stores. Like, why did we go build this thing? I'm going to do a live demo, which is always exciting. And then I'm going to talk about the optimized row columnar format. This is sort of the technical part of the talk, or ORC. And that's the file format that we use to actually store the columnar store on disk. And we'll talk about what it looks like, how it's different from row stores, and what benefits we get out of ORC. ORC's actually an open source format that was developed by Hadoop and Facebook, or sorry, Hortonworks and Facebook for Hadoop. I'll talk a bit about what we get out of Postgres, some of the benefits that we get from working with the foreign data wrapper system and the Postgres engine. And then I'll present to you some benchmark numbers, mainly focused on performance, but some I/O ones too, showing what we get out of the columnar store engine. All right, so first, why did we go build a columnar store? This is probably when the idea sort of started rising in volume inside our company. Is we had a customer come to us who had a table that looks like this. They were like a retail customer, and they basically had 30 million items that they had sold, stocked, or interacted with in some way before. And they had around 700 columns in this table. Things like, you can see IDs, pretty normal. Size, length, height, color, last sale date, first sale date. When I saw this table for the first time, I thought, oh my god, this is the biggest table that any could ever possibly imagine. It turns out this is just sort of on the large end of tables, but not definitely in the biggest possible end of tables. So with this table, though, they had 700 columns, 30 million rows, and they were running queries like this. Relatively straightforward stuff, like give me the average, give me the max for a subset of my items, apply some grouping. Nothing that's touching 500 rows or anything approaching the 700. So how does that query get answered if you're using something like Postgres or other row-oriented stores? Well, what happens is your database will go read that data off of disk or wherever it's stored, and it'll read off a row's worth of data. Then it'll pull out the actual column values that it's interested in. It'll decide whether to filter or not that row. And then it'll maybe do some aggregations if it's not going to get filtered. And it'll do that for the first row. It'll do that for the second row, third row, fourth row, and so on until it's done. So what do you notice there is you're actually reading all that data off of disk instead of just the 5 columns you're interested in. So in our case, this meant for the query you saw, we were doing roughly 39 gigs of unnecessary I/O. And that sounds like a big number, but to put that in context, if your table is out of memory and you're getting sort of a typical memory speed, you're going to take an extra 3.9 seconds to answer that query. If your table's coming off of an SSD, it's going to take upwards of 60 seconds. And if you're on a rotational disk, it's going to be even worse than that. So latency was the big thing that probably drove us towards columnar stores and reducing I/O. And so how does this work with a columnar store? Well, we're able to take that query, and your database already does this. It identifies which columns are involved in that query. It says, hey, I've got an ID, a price, a quantity, a last stock day, and a weight. That's what I'm interested in. And then a columnar store will lay that data out sequentially on disk. So instead of reading a row at a time, it'll first go and it'll say, all right, give me the values for the ID column. It'll read all of that off of disk in one pass. Then it'll go read the price column off of disk in one pass. And this is a bit of a simplification. We'll get into how these reads actually happen later on in the talk. But you'll notice here, we skipped over the size column. And then it'll read the quantity, and so on. So the big motivation for building the columnar store was to improve latencies by reducing I/O. And we do that by reading a subset of columns, as opposed to reading the whole set of data we need off a disk. But there's some other benefits, too, that I didn't get into. And the main one there is better compression. And the reason you get better compression when you're using a columnar store is typically if the data is laid out on disk in a row format, you're going to have values that are not necessarily related to each other next to each other. So you can imagine if I have a color attribute with each item, I would have a color attribute, then I would have 699 other attributes, and then I would have a color attribute again. And when I applied compression, there'd be a lot of space between the color attributes of unrelated things. Whereas if I apply compression to values that are laid out adjacent to each other, there's going to be a lot more colored reds in each block I'm compressing, for example. And so you'll see better compression ratios, which will in turn result in you having two auxiliary benefits. You'll actually need to buy less disks, and this can be a big win for you if you're paying a lot for SSDs or for big external storage devices or something like this. And it means that you're not only saving memory by just, saving I/O by just reading only the columns you need off a disk, you're actually going to read compressed data off of disk. And it's going to be well compressed. And so that means you'll do slow I/O, or relatively slow I/O, on limited amounts, and then you'll decompress it in memory where you get that faster read bandwidth. Okay, so now that I've gotten you motivated, I'm going to go through and I'm going to give you sort of an overview of a live demo of how we work with, how I set up the columnar store. And sorry, it's frazzled because I think I got the second version of my slides, so some of this is going to look a bit weird. But yeah, so right now what I'm going to do, this is actually the GitHub page, which is where the columnar store is managed. It's an open source project. Under the Apache license, we get contributions from the community, and we contribute our own. And so I'm going to walk you through getting this, building it, and installing it, and then loading some data into it. I'll show you some queries using it, and then we'll jump back and talk about the other topics. So how many people here have built an extension before for Postgres, installed it? Okay, so a bit more than are familiar with foreign data wrappers. So I'm going to hop over here. Is that font big enough that everyone can see it? Maybe I can make it a bit bigger here. Is that better? All right. Okay, so let's start. So I'm going to go into the foreign data wrapper directory here, which is where I've checked out the code already. Oh, and you can see I already made it. So I'll clean this up. Oh. And so making an extension for Postgres is actually probably the trickiest part of using an extension. So this is where you need to pay attention, and the rest is pretty straightforward. So to build it, the first thing you're going to do is just use the regular make command. And the trick with making is you're going to need to make sure that the PSQL you want to link against, the Postgres install, is on your path. So you can see there at the top, I have like the bin directory included on my path in front of anyone else. So that's the version of Postgres it's going to link against. And then after I've built the library, I'm going to install it. You typically do that as root. And so then that's all done. It's now made. And so the next step is going to be just like any other Postgres database. I'll go and I'll init my DB. Okay, so this is just like anything else with Postgres. And then the only other hiccup here is with CStore, FDW, and some other extensions that hook in different ways, you may need to edit the config file. So we're going to do that here as well. And so what we're going to do is, I'll show you, but we're going to edit the shared libraries preload configuration. And we're going to make sure that CStore FDW gets loaded on startup. And this is just so we can hook into the copy command in a specific way to load data into the extension. So you won't need to do this for every extension you need to build, but you will need to do it for us. Okay, and so now that that's done, I'm going to go ahead and I'll start up the database. Oh, by the way, if there's any questions, I didn't say this at the start, but feel free to interrupt. I'm happy to take them. So database is now started, and now I'm just going to connect with my regular PSQL session. Okay, so everything looks good, no relations here. What I'm going to do is I'm going to go create my extension. And so this will basically run some initialization scripts that are in the extension to create some configuration, and I think it might validate the libraries actually exist. And then the next thing to do is, wrong window, is to run this command, which is going to create some shared resources that can be used across instances of the extension. For us, this doesn't really matter, but you can, question? That is a good question. I think it's used across schemas. I think it's just going to be, like, I think you could probably run the create command wherever you wanted. I think it's like a global object, but I'm not sure on that, to be honest.
No, I mean, when you did the create extension,
yeah. Yeah, I don't know. I was under the impression that extensions were available across schemas, but I don't know. Okay. Yeah, I don't think we have any support for that right now, as far as I know. Yeah. But we do accept feature requests on the GitHub page. So yeah, this is, and then we can create the server here, you can see. And then after that's done, like that's all the setup we need to do, and then we can start creating foreign tables. And so here, wrong window here, I'm going to show you how to create a foreign table. So I'll just grab all this stuff here. Oh. There, that's the excitement for you. Okay. So here you can see what creating a foreign table looks like. And this is true whatever sort of foreign data wrapper you're using. The real big difference is you can see at the top there, we say foreign table instead of just table. Otherwise, the actual like schema of the table looks the same. And then there's some additional options that happen at the bottom. So you need to specify the server you want to use. And that's the one that we named in the earlier create server command. And then you can pass in some options. For us, there's two options. One is if you want to enable compression or not. And so here you can see we've turned on PGLZ compression. And I'll talk a bit about what that means later. And then we also have an option to give a directory of where you want to store the Columnar store form files. And by default, we'll just pick a directory inside your data directory and put them there. Actually, I don't know if that's, we won't just pick one. There is a directory, we'll put them in there. I just don't know what it is offhand. And so yeah, so this is all that needs to happen. So I'll run that command. I think we ran that command. Let's see. Nope. I don't know what happened there. There. So now we've got the table created. You can see it exists. And now before we load some data in, I'll just show you sort of, this is the data that we're going to load in. We've got about 720 megs of data from a line item table. And this is part of a TPCH benchmark, which I'm not sure if you guys are familiar with this, but it's a popular benchmark for decision support databases or data warehousing type workloads. So we generated a bunch of data with it. Looks like this. We're going to load that data in. So loading that data in is pretty straightforward. Right now, the only way to load data into your Columnar store is to use the copy command, and you can see it running here. You can't do insert or update today, and I'll talk a bit more about that later on in the talk too. So while that runs, we'll actually jump over. Like any good TV chef, I've got another version of this database preloaded with this data. And so you can see here, I've actually loaded that same file into 3 different tables. So at the top there, you can see a CitusDB CStore line item table. So this is like using CStore with Citus, which was the change in my slides that somehow occurred during the PowerPoint crash. And then there's the CStore line item table. So that's the data just loaded into a single foreign table using CStore. And then there's the same data loaded into a regular Postgres table. And so I'll just show you guys some quick queries running across these different tables. Oh, that's the load still happening. So here you can see we're just going to count the items in the table. And Postgres is chugging through it, 5.7 seconds. And then we'll repeat this for the other tables too. So this is the same command over CStore table. So you can see here this is 1.5 seconds compared to 5.5. By the way, you shouldn't trust these numbers. I'll show you some real benchmarks later on. This is more just sort of general look and feel since this is happening on a MacBook Air. But okay, and then so CitusDB, I didn't get the chance to tell you much about this, but basically we're able to run a distributed version of this database, and this is just running on my laptop, but this is just able to use multiple C stores at once across all the cores on my laptop. And so that's able to drop it down even further from that. And so count's not an especially interesting query, so I figured I'd show you one that's actually a bit more real. So this is just an average over, for example, an average over the prices for these items. So with Postgres, this one actually usually takes around 15 seconds. So if you want to get to know your neighbor, talk about how you didn't want to have that second drink last night, now's your chance. Yeah. All right, yeah, so 16.4 seconds. And so then you can see sort of there's a similar story here with CStore, although, and we'll get into sort of the different performance depending on which type of query you're running. Oh, sorry. But this usually takes around, I think it was like 10 seconds basically for CStore. And so that's, now we're just pulling out just that one column, computing the average over that, as opposed to pulling all those rows off of memory or SSD in my host. And then you can see the same thing using Citus, and Citus is going to be even faster because it benefits even more from having parallelism when there's actually compute involved. And so here you can see that's taking like 3.3 seconds. So that's how you sort of set up CStore. I didn't get into the Citus part, but CStore is as easy to set up in the distributed database as it is in the local one. So now we'll hop back over here. Maybe. All right. Yeah. So the benefits of using the foreign data wrappers are that you get to use all the types that Postgres has, which I don't know if you guys were in Jonathan Katz's talk yesterday, but there's a lot of them. I learned a lot of new ones there. You can use all the user-defined types, all the existing ones. You can use all the query language. It just will work.
So can that columnar build on like complicated types, maybe arrays, even?
Yep. Yeah, any type Postgres can handle, the storage can handle, the foreign data wrappers and the Columnar store can handle. Yeah, no, that's fine. Yeah, so there is things like indexes. We have a type of indexing called skip list indexing, which I'll get into later, and that's actually part of the orc format, and we use that. Although, yeah, it helps. It's more, like I said, this is more targeted for analytic queries and sort of looking up individual key value pairs. So the indexing helps you, but it's not going to be as robust as Gin or just indexing, basically, that you get out of Postgres. All right, so state of the columnar store. So I'm going to talk a bit about how we built CStore FDW, why we made the choices we did. So when we went to go build this thing, we sort of stood up and we looked around and said, what's going on out there in the columnar store world? And we took away sort of 3 learnings from looking at the existing products and solutions out there in development. The first one was that a popular approach at the time was to take an open source database, sort of fork it, swap in your columnar store engine, and then never look back. And so the downside to this is that you don't get to pick up any of the bug fixes that come along, any of the new feature development that comes along. If there's new client-like versions that come out or stuff like that, they may or may not work with your library. So this wasn't appealing to us because we were already working with Postgres on Citus and able to rebase against the new versions of Postgres, and that was a huge value to us and to our customers. And we didn't want to lose the benefit of the community. The next thing we noticed is looking around is that there was a lot of actually open development going on columnar stores. In fact, there was a number of great ones being built for the Hadoop Distributed File System, or HDFS. And as I mentioned, Orc is actually what we settled on, and that's the second generation of columnar formats. And that was built in a collaboration between Facebook and Hortonworks. They published academic papers. They invited community contributions. It was well thought out, and we said, we don't need to reinvent the wheel here. And then the third thing was that, hey, at the time, the PostgreSQL extension machinery was taking off. People were building external storage to hook up to other files, to hook up to other databases, to build in-memory storage systems, that sort of thing. And as I mentioned, if you use the foreign data wrapper technology, you get a lot of benefits from Postgres if you're willing to follow that API. And so we decided to move forward using approaches 2 and 3 and combine these 2 to create a solution that we thought would work well. So I'm going to talk briefly and a bit technical about the orc file layout. So this is called, orc stands for Optimized Row Columnar Format, and this is the file format that the people at Facebook and Hortonworks developed, and which is what we use for writing out our CStore files. And so this format gave us 3 benefits. The first one is the one I just discussed earlier, is that, hey, these columns are actually laid out sequentially on disk. Like you're not writing out data row by row, you're instead writing it out column by column. And Orc actually does something called horizontal partitioning first. So you'll have like a batch of, say, 100,000 rows, and you'll break it up by columns inside those 100,000 rows on disk. And I've got a diagram on the next slide that will sort of go over a bit more in depth. Compression. So Orc enables you to configure compression on a per column basis, and does it on blocks of data as well. So we'll talk a bit more in detail about these 2 later too. And then skip indices are the other ones. This is the indexing solution. And so skip indices basically allow you to keep a min and max value as well as some counts for blocks and use those to filter out portions of your data during queries as needed. Okay, so this is a diagram which shows you the Orc file format. And this is actually from the Hadoop website. Like this is their architectural diagram. And so you can see here on the left, that's like the file, basically. You can see from like byte 0 down to byte n. And you can see when I talked about horizontal partitioning, what I'm talking about is these blocks of 150 rows up there. And so those are called stripes. And so each stripe will have a collection of index data at the top. That's the green stuff. And that's going to be the skip list index information that I told you about. Then inside, it'll have the blue section, which is the row data. And then at the bottom, there'll just be some footers to sort of validate that you've reached the end of the stripe, that sort of thing. And then you can see how the columns are laid out in here. So each of this row data section maps to this stuff. And so you can see for those 150,000 rows, I'm going to write out all of the values for column 1. Then I'm going to write out all the values for column 2, for column 3, and so on. And then in like what this actually maps to is these chunks of 10,000 values for a column. And those are basically the atoms of the Orc file format. So skip list indexes apply to blocks. Compression is configured on a per block level. This is sort of the building block of the file. And so these things are the default values I've listed here that we use. These are just configurable in your Postgres configuration if you want to, whatever values you want. Oh, and then the other thing I would add is the index data is actually the skip list index, or we store those using Google protocol buffers. And so that helps us a lot because it gives us a good versioning system. So if we want to improve the indexes and add more information in there, the libraries are able to handle that. And you can imagine doing like things where you pre-compute the sums or the averages as well or stuff like that over these blocks, and you're able to use that information when you're answering aggregate queries as well. So I said I'd talk a bit more about how compression works with CStore, and so this is that. The current compression mechanism we use is the PGLZ compression mechanism, which is actually built into Postgres. And I'm not sure how many of you are familiar with the toast tables in Postgres at all. Yeah. So these are tables that are used to store large values in Postgres. And then they link to them from your actual physical real table. So we use the same compression mechanism that they use in that table. The benefit that we get, and the reason you'll see better compression than you will with toast tables, is because we're compressing like 10,000 related values at a time, whereas a toast is only getting to see one value at a time when it's doing its compression. We added in all the plumbing for compression to add new compression types if you wanted to. So things like Jiffy or PG or diff listing compression, stuff like that could be added in on. You can configure that on a per block level too. But we haven't actually taken advantage of that, and we'll talk a bit about like what the future directions are and possible extension areas. But the plumbing's all there to be able to configure arbitrary compression schemes. So how good does compression actually work? How much win do we get out of PGLZ? So this graph actually shows you us running through a bunch of the TPCH data that we built, so 10 gigabytes of TPCH data, and this is the benchmark data that I told you about before, and we loaded it into our other table. And you can see that we had 5 tables here. One is the line item table, the orders table, the part supplier table, and the customer table. And they all sort of compress at different ratios, some more than others, but on average you can expect like a 25% compression ratio. And so what does a 25% compression ratio mean for you? Like what's the big win there? It depends a lot on like what your workload looks like. If your data already all fits in memory, compressing it more is going to help you not in terms of speed, but it's going to help you be able to scale more. Like before, if you had to have 8 gigs of RAM on your box to store 6 gigs of like data and query it effectively so you never went to disk, after compression, you may be able to fit an additional 4.5 gigabytes of data on that box and still see similar performance characteristics. If you're going to SSDs, It's going to mean you'll be able to buy less SSDs. And SSDs are fast, but they're still not as fast as memory, so you'll be reading off of the SSD less. And then perhaps most importantly for Citus, and I'll get into this a bit more of later, I hope that's where those slides ended up, is that you'll be using less disk bandwidth. So often if you have a lot of appliances on this box using the disk, you may end up bottlenecked, not just on I/O for your database, but on I/O for your other applications that are running there too. And so you'll be able to reduce that. And for hard drives, the win is obvious. It's going to be much, much faster if you read less off of a hard drive. And you know, we've definitely talked to people that have like these expensive external SANs that run off of hard drives, and there you'll be able to buy less storage as well.
Does the I/O use the same sort of typical I/O pattern that PostgreSQL normally does, where things will manage shared buffers?
We actually get to bypass, oh, sorry, I'll repeat the question since I haven't been doing that. So the question was, does the I/O follow the same pattern that Postgres' typical I/O does, where it lands in shared buffers first and then makes it into other areas of the application after that? We actually, by being part of the foreign data wrapper technology, we're able to bypass the shared buffers section. You handle your own I/O down there. That's actually been a bit of a win for us. There's a patch out there for review right now about the way shared buffers are managed, and there's definitely some suboptimal behaviors there when you have high concurrency.
Does it still end up, though, in the operating system file cache?
Yes, it'll end up in the operating system file cache, but it won't end up in the shared buffers.
Okay.
Yeah. So I talked a lot about what the positive sides of Orc were. Like, what are some of the drawbacks of Orc? Well, first, there's support for a limited number of data types. Like, compared to Postgres, I think they have like 10 to 15 data types defined in Orc. There's like a couple ints, a couple floats, a Boolean, a text field. Actually, there's a couple kinds of text fields. But, you know, there's no ranges. There's not a lot of dates. You know, I learned about IP addresses yesterday. There's no user-defined types. And then the other problem is they don't have the sort of constraint exclusion mechanism that Postgres has. So each time you want to add a new type to Orc, you have to write a whole like bunch of code to handle the constraint exclusion for that type. By like using Postgres' serialization and type system and constraint exclusion machinery, it made it really easy for us to handle all the Postgres types. And then the other one that is missing from Orc is the statistics machinery that Postgres has. So if you use the foreign data wrapper technology, you can implement a statistics API, and then your wrappers will return back a sample of the rows to Postgres, and you'll be able to make intelligent decisions about query planning. And so things like joins will occur in the right order. You'll be able to get good cost estimates. There's just a lot of good things that can come out of getting you good statistics. All right, so now on to the money, the benchmark results. So we actually ran our benchmarks recently, and we did them using the TPCH benchmark. I mentioned this before. So it's a benchmark that sort of is designed to simulate almost like a factory environment. There's sort of customers, there's parts suppliers, there's products, that sort of thing. We generated 10 gigs of this data using their tools, and then we loaded it into Postgres running on 2 EC2 instances. And so the reason we used 2 different types is so we could test it on a hard drive and an SSD. And then the tests were done where the data was at rest on disk, where it wasn't sort of read into memory. And then we have another test that'll show you where the data is resident in memory. Because if you have 10 gigs of data, it's probably always going to be in memory. And then we compared sort of a vanilla Postgres install to something using CStore for this data and something using CStore with compression enabled for this data. And so I'll show you a preview of this slide. Uh-oh. That's weird. All right. Okay, we'll skip the one that has the hard drive. So this is the SSD. The hard drive had even more drops. The hard drive was right in. So this one, you can see here, is the blue bar represents your query times with the regular Postgres. The orange bar here, or red bar, actually represents it using CStore. And the orange one represents it with CStore with compression enabled. So you can see here, like higher query times are the bigger bars, lower query times are better, which are the ones that are closer to this. And then each of these groups is a different query in the benchmark. So the benchmark's made up of a number of different queries. So basically, with compression enabled and with CStore, you're speeding up, nearly all the queries. The improvements are roughly in the sort of 25 to 50% range here. Unfortunately, we lost the slides from the hard drive version. Those are roughly in the sort of 50% range is probably the average improvement there. And then you can see here, so this is I mentioned before about one of the other benefits was that you're going to sort of reduce your disk I/O and like how much time you're, not how much time, but how much I/O you were using off of your disk. And so here you can see we actually used I/O top to measure the amount of I/O while we were running these queries. And you can see like on various times we have huge reductions from just using CStore and even bigger ones from using compression. So for example, if we look at query 6, we went from 9 gigs of I/O when we're using Postgres to 1.8 gigabytes when we're using CStore, and all the way down to 0.8 gigs with compression enabled. So that's like 10% almost of the original query size. Oh yeah, and to put some of these numbers in perspective, I do have some statistics here. So query 6, for example, here is a 26-second query that went to 14 seconds, and query 3 was not as much of a win, but still a big win, from 37 seconds down to 26 seconds. All right, so and this is the less exciting graph that I promised you as well. So you might be saying, hey, this graph doesn't look great, and you're right. When you run compression on data that's already in memory, you're not going to see a huge win out of that. So here you can see it's basically a wash on average if you enable compression on data that's already resident in memory. And so the big win, as I said before, if you're going to use compression on your data, is you're going to be able to fit more data in memory. So we're getting, now you can fit like, 3 times as much data if you're getting a 25% compression ratio in memory and still see these query times. So if you don't compress, you'll still see an improvement. But if you're compressing in memory, like you're just spending CPU cycles on the decompression that sort of makes it come out even. All right. So I spoke a bit about CStore, and the question you might be asking yourself is, why did Citus decide to build CStore? And so I mentioned that I work for a company called CitusDB. We build a product called CitusDB. And what CitusDB is a scalable analytics database that extends Postgres. So analytics is one of the areas that sort of our product intersects with CStore. And the other one, and I'll explain why this is important to us, is that we end up bottlenecking more often on I/O than regular products or other Postgres databases because of the amount of concurrency we're able to do. So what Citus does is we're able to, when you're loading in your data, we automatically will shard it across a cluster of machines, manage tables that are installed on all those extended Postgres machines, and then we'll do replication for you as well. The difference, one thing that we aren't, is a fork of Postgres. We work through the extension machinery, but we have some like coded in hooks. So we do sort of build a separate RPM that we distribute. We're not just an extension that you can install on your own, but it does mean that we rebase every year to the newest version of Postgres. So last year we released Citus 3.0. That was 9.3. This winter we'll release Citus 4.0, which will have all the features from Postgres 9.4. The advantages of being on the newest versions of Postgres are you can use all your favorite data types, all your extensions. We have people using CStore with Citus. We have people using things like PostGIST with Citus. We have people using the HLL extension with Citus. All this stuff just sort of works because we're just another Postgres extension, really. And so this diagram is meant to sort of quickly show like what the Citus architecture looks like and how CStore would fit into it. Each of these boxes is a machine in your cluster. When you load your data into Citus, we'll automatically break it up into these small chunks called shards. And these shards are the yellow boxes, and those will get distributed out to all the nodes in your cluster. And they'll also get replicated subject to some configuration. So you can see here we have like an A over here and an A over here. So configurable replication factor, that data will get pushed out to as many spots as you want. Because we're very, again, Postgres friendly, all these things are just regular Postgres tables. So for example, the placement metadata and the shard metadata is just a catalog table that you can query on the master node. And all these tables on the shards are actually just regular Postgres tables on these extended Postgres databases running on your clusters. And because they're just extended Postgres databases, we can use CStore with them. So if you create a table on your master node that is a foreign table, and you also apply or distribute by clause to it, it'll get pushed out as CStores on the other workers. You could use other foreign data wrappers as well. And so the reason that CStore was especially appealing to us is because a lot of our customers have these big machines that have 24 cores on them. If you're running Postgres regularly, one query can run on one core at a time. Whereas if you have Citus, your query will run on all 24 cores at once. And when you get into that world, you can really quickly saturate your I/O bandwidth. So the disk bottleneck issue was a big one for us. So sort of reducing the amount, that big drop we saw from sort of 9 gigs to 2 gigs to under a gig of I/O for a lot of these tables, that was really important to us. And so that was what made this extension really extra appealing to our users and to us. So as I mentioned, CStore is an open source foreign data wrapper for Postgres. It's been around. We launched, I think, in March of this year. I was actually at PGCon NY when we launched, but didn't get to talk there. But we recently, in August, had our 1.1 release. You can follow all the releases online at our GitHub site. That's github/citusdata/CStore foreign data wrapper. And the new features in the 1.1 release included improved statistics gathering. So we had some issues with the way we were estimating, and we weren't covering all the estimates that we could. Then automatic management of table file names. So before you would have to, like, when I created that, you saw I just had to specify the compression type I wanted as an option. Before, we would make you create a directory and make you pass it in as an argument. Now the default is that we'll just create that file for you inside your data directory. And management of table file data. So now if you sort of drop your foreign table, the data will get cleaned up automatically afterwards. So this release was mainly about the statistics and then improved integration with Citus to make it easier to use in that world. We've got lots of future work planned. So one is improved memory use, and that's actually planned to come with our fall release, which is coming up this fall. The other things we're looking at are native insert, delete, and update support. This is actually a tricky one. Like right now, you can only load data, as I said, through the copy command. Just the way data is laid out on disk in columnar stores, where you've got one column followed by another column, mean that it's much less efficient for sort of arbitrary writes into that database than it would be in a row-oriented store. But there's still ways to do it, and we've definitely heard from a lot of users that this is something they want. We're looking at ways to improve read query performance. We actually had an intern over the summer who ended up working on this for about 8 weeks, working on vectorized execution there and building some prototypes where we would process batches of values for aggregates in the Columnar extension. So when you wanted to compute a sum or an average, instead of calling the average function once for each row, batching up 100 or 1,000 values and passing them off at once to be deaggregated. And we saw actually some promising results there, so that's something we're definitely going to be looking into. As I mentioned, supporting different compression codecs. We spent a lot of time laying the groundwork to let us do that, but right now we don't have support for any other codecs except for PGLZ. There's lots of other great ones out there, like Google's Jiffy comes to mind. There's also cool things you can do with things like diff list compression, where each value is just stored as an offset from the previous value, or like the number of repetitions of a value in a row. You can just store repeated repetition as compression. And there's lots of other feature requests on GitHub. I encourage you to come out there and participate in the discussion, or even better, in the development. So we're almost at the end, so I just wanted to summarize everything we went over here. So CStore is the open source columnar store foreign data wrapper for Postgres that we at Citus have built. It targets analytics workloads today. It's going to give you 3 things. It's going to improve your query times. It's going to reduce the amount of disk I/O you need to do, and it's going to reduce the amount of disks you need to buy to store your data. CStore FDW integrates with the foreign data wrapper APIs, which means you get a number of benefits. You get to support all your Postgres data types that exist, all the new ones that you want to create, and all the new ones that get created. JSONB will work just when 9.4 comes out with this. Statistics collection, plugging in through the statistics API means we get great query plans when using CStore FDW and good estimates. And then because it's a foreign data wrapper, it means it's relatively simple to set up and run on your Postgres instance. You just basically need to load the extension up, create a table, copy your data in, and you're done. All right, I think we finished up pretty early, so.
So if we want to join this table to some other tables, no matter if it's the same type of columnar table or some other normal PG table, Postgres tables, if we analyze the tables, get the statistics, and we check what will be the difference we will see, look at the sprint plan. What's kind of result?
Yeah. So the question was, what's the analyze output how is it going to differ between sort of a regular Postgres table and with CStore?
If you join them together.
Yeah, and if you join them together. So the data that's going to come out of it is going to be useful for knowing like what the cardinality is of the CStore. So basically, the statistics API will hand you back a sample of the rows. So basically, Postgres will come to us. It'll say, hey, give me a sample of this size, a random sample of the rows in your table. Postgres will be able to use that information to decide what order to join tables in. You won't see things, for example, like our indexing, our skip list indexing. I don't believe that will show up in the analyze input. Like, it won't know that, but it'll know roughly, be able to make cardinality estimates and sort of row output estimates from the statistics. Oh yeah, it will be able to. I wouldn't even say most likely. It will be able to, yeah. Yeah.
Just real quick, I saw you were using 9.4. It doesn't require 9.4 though.
No.
Okay.
Yeah, this is, yeah. That was actually me trying out 9.4 a while ago, and I haven't gotten rid of it. Yeah.
ORC, you actually collect the min, max, and store it as well, right? As part of it.
We don't do that today. We could. Oh, sorry, I lied. We do store that today. We don't let you leverage that, for example, in aggregate queries. For example, if you want to do the max, like, we aren't pushing down the max function, but actually, foreign data wrappers don't easily push down the max function to the foreign data wrapper level. So we're not able to say, for example, like, hey, I need the max. Just I only need to read the skip list index.
You still read all the rows.
Yeah, you would still, yeah. And the same for, like, you could imagine things where you would read the sum out of there too and stuff like that. So definitely some of the prototyping we did with the vector execution required some hooks back into Postgres, or sorry, I think hooks into the extension from other areas of Postgres to be able to do this vectorized aggregate queries. And so we're getting more comfortable with that, and that would be something that would definitely be possible for the future.
So I have event data that's streaming in, thousands of things happening per second.
Yeah.
Then I have to load this then into C-store. Is it possible to do that incrementally, dynamically? Does it all have to be in there at once?
Yeah, you can load in incrementally. Probably the easiest way for you, so one thing is if you're using Citus, like, you'll be able to just load this in and we'll create individual little C stores for each of the chunks of data as they come in, and then you'll be able to query them like a big table. But yeah, you should be able to copy in more data into your existing C store as well.
Okay, are there performance penalties for doing that?
No, I mean, there's performance penalties associated with, for example, like compression. Compression will cause your loads to slow down. They'll be faster without compression. But I don't think there's any performance penalties associated with, like, the incremental data loads. All that compression is on a per block level. So it's not like you're recompressing the whole file each time you load into it. You're just compressing each of the 10K blocks or however big your block size is as it gets loaded.
What about runtime? Is there a runtime penalty for loading a day's data and then the next day's data, next day's data, querying across the time?
No, I mean, not associated with the incremental nature of it. Obviously, if you're doing a sequential scan across more data, it's going to be slower. It's not going to make a difference whether you loaded that data all at once or in sort of 100 different chunks.
Well, okay, to make my question a little more clear,
Yep.
the way I'm thinking of it. So I've got 3 days a day.
Yep.
Load it Monday, Tuesday, Wednesday, and
Yep.
then run a query.
Yep.
As opposed to load the whole thing on Wednesday.
Yep.
Run the query.
Those two queries should be the same.
They'll have roughly the same.
Yeah.
Okay.
Yeah.
But at current stage, if you have to load 3 times, you got to load 3 different tables, right?
No, I believe you can copy into an existing table. Yeah.
It looks like it's striped anyway, so even if you load one day of data, it's going to break that up
Yeah.
into blocks. So when you load the second day, it's still going to be breaking it up into blocks. You might end up with one small block at the end,
Yeah.
like one small stripe, but it should be
Yeah.
pretty linear.
Yep. Yeah. There's nothing that we've heard of about performance penalties there.
Okay.
Hopefully, Hadi will be able to make it next year to answer your question in more depth. Any other questions out there? Yeah.
Okay, so I'm more of a web guy.
Yeah.
I don't, do the data analysis or anything, so I'm probably the wrong audience. But are there any workloads or types of queries that this would be slower for, or is it just like always faster?
There are definitely workloads where it'll be slower for. So, for example, if you want to select a single key, like if you're looking for a single user ID from a table of users or a session from a table of sessions, the skip list indexing is not going to be as efficient as like a gin or a gist index at retrieving a single row. Like, you'll still have to scan through all these indices in sort of a linear way through the relatively small index blocks. Like, it's not going to be as slow as scanning the whole table. The indexing's helped you, but it doesn't help you as much as gin or gist, for example.
Just to be clear, I mean, it's still a range index
Yes.
So once it gets you to a block, you're going to have to scan that whole.
Yep. Yeah, that's right, the 10K value. So there's sort of some trade-offs there in terms of block size and like, yeah.
Great for analytics, terrible for OLTP.
Yeah. Yeah, even ignoring, well, the bigger issue with OLTP, I think, is you can't do, like, there's no transactional stuff, but yeah. But yeah. Any other questions? All right, great, thank you, everyone.